Welcome to video 12.1 in our first Principles of Astrophotography series. In this video we discuss the field of view and show how to calculate it.
The field of view plays a key role in determining the suitability of a particular telescope camera combination for a particular celestial object. Some objects occupy very small regions of the sky and are best suited to telescopes with long focal lengths, while others occupy huge swaths of sky and are best suited to short focal length telescopes.
This video is based on section 12.1 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. Principle 128, this is where the real, true principles of astrophotography, all the other ones were true too.
But this is where the rubber meets. This is really important in framing your subjects, is to know what your field of view is.
All the work we've done to get pixel scale and everything up to this point comes to a head. So, field of view, definition. The field of view, length times width of a telescope camera combination, is the angular length and angular width of the region of sky that are imaged by this combination in degrees.
So you can measure them in arc seconds, you can measure them in arc minutes. We just do them in degrees for consistency. So the idea here is that this length here is measured in degrees. So it might be 1 degree or 2 degrees or half a degree. And this width is also measured in degrees.
The length and the width are measured in the sky, not on the camera. Right? Yeah. We're talking about the sky.
We're talking about the sky. So we're talking about how much of a rectangle we're getting of the sky.
Yeah. Mm-hmm.
And that tells you, if you're shooting the Andromeda Galaxy, you need about 3 degrees, right?
Yep.
Yeah, etc. Okay, calculation.
Field of view calculation. To find the field of view, multiply the sensor array dimensions, length and width in pixels by the pixel scale, which we figured out before, and divide by 3600.
So here's how it goes. Let's just do it for our 6200 mm Pro camera. The length of the pixel array is 9,576 pixels.
Oh, love it.
It's just a number that rolls off the tongue so easily. And then the width is 6,388. If you multiply these two numbers together, you get 61 megapixels. That's what we mean by multiplying the length by the width gives the area measured in square pixels. So, given those two numbers, we want to try and figure out how much sky this is going to capture. Luckily, video 6.4, we derived the pixel scale equation that Ren mentioned earlier. It's that number 206.3 that we derived times the pixel size. Of what? Of the camera. Divided by the focal length of the camera? No, of the telescope.
The camera doesn't really have a focal length.
No, it doesn't. Yeah. It has to have a lens in front of it. I mean, some cameras that you would buy, your iPhone camera has a focal length because there's a lens in front of it, right? But usually you buy a camera without a lens and then you screw the lens on there, right? At the higher end cameras anyway. Yeah. So we have properties of both the camera and the telescope that tell you what the pixel scale is. And that gives you, if you plug in the numbers for our Edge HD 9.25, which has a focal length of 2350 millimeters, the pixel size of our camera is 3.76 microns. Then you get the pixel scale, aka the image scale, aka the plate scale, aka resolution of the camera telescope combination. There's a million names
Ad
people use
nauseam,
for it.
yeah.
Ad nauseum, yeah. But we call it the pixel scale or the image scale. So in this particular case, each pixel on the camera, so I'm going to take, we're going to have pixels on the camera. Each one of these images is 0.33 arc seconds of the sky. Well, if each of these 9,576 pixels images 0.33 arc seconds, then if you multiply 9,576 by 0.33, then you should get how many arc seconds across the horizontal of your telescope. And that would give you a number in arc seconds. But normally, it makes sense to convert that arc seconds into degrees. And if you remember, there are 60 arc minutes in an arc second and 60 degrees in an arc minute. And 60 times 60 is 3,600. Yeah, here's the calculation right here. The pixel scale, the length in the number of pixels horizontally, then divide by 3,600, this conversion factor. Then if you just check the math, you get about 0.87 degrees. So that telescope with that camera will image about 0.87 degrees in the horizontal direction. Then you do the same thing for the vertical direction, you get about 0.58 degrees. Pretty simple calculation, really,
Sure,
right?
simple.
Yeah. Are you bored?
No, I'm just,
You're just saying that's
everything you say is simple is not always simple.
Well, that's simple though.
Well, you had to take 3 steps just to get from the pixels to the degrees. But you didn't even show. It's simple though. It's
well,
simple.
I just took this number and I put it in here, and I took this number and I put it in here, and I divided by 3,600.
Okay.
So that's that one. That's how to calculate it. But when you know how to calculate it, then you have the power. Because if you buy a new camera with a different pixel size, you just plug it into here, and boom.
You buy a new telescope.
You buy a new telescope or whatever. So that's one reason why in the book we have a table in the introduction with the telescopes, the 8 telescopes that we were planning to buy at one point, but never did. And then after those 8, the telescopes that we did actually buy, but in there we have the field of view of all those telescopes, so we can say, okay, this is the one we need to shoot this object, et cetera, et cetera.
It's an easy reference too. So once you've got your field of view, that it's a lot easier. You can get onto Astrobin and see the photos that are on there, see what their field of view is, and then compare it to your field of view of your camera and say, this is a good field of view for mine, or maybe this won't work, or I need to switch out for another telescope that'll work better.
Yeah, and if you're choosing which object you want to shoot in August and you're faced with some clear nights, then and you have this particular focal length of telescope and this particular camera, then you want to look for objects that you're interested in, but also that'll match your field of view pretty well. Okay, so we just calculated the field of view measured in degrees in the sky. So in this particular case, it's 0.87 degrees horizontally and 0.58 degrees vertically is the bit of sky that you're going to be able to see through that telescope camera combination. Then what happens is in video 5.1 we talked about how to calculate the linear, so this right here is what we call the field of view, in degrees by degrees. And then this L tilde, that little squiggly line above here, is called a tilde in physics, are the linear dimensions of your camera sensor. And there's a typo right there. There should be millimeters. In the video 5.1, we talked about how to calculate those dimensions. And those aren't hard to calculate either.
Good.
But basically what we're taking is this little region of sky and we're translating it into a sensor. And if you might remember, our sensor is 36 millimeters, or 3.5 centimeters by 24 millimeters or so. 36 millimeters. It's a big sensor, no doubt about it. So you're taking this region of sky and you're translating it onto a sensor of that size. Yeah, no big deal.
Easy peasy. Principle 130, field radius. The field radius is half the diameter of a circle that passes through the four corners of the field of view.
This is one of the things that when we first got on Astrobin, we were admiring all the photos, but everybody, so he lists the field radius, and I was poking all around, what in the world is a field radius? Do you remember wondering about that too?
Yeah.
And it's not hard to find, and he posted on his website, but all it is if this is the field of view measured in degrees of sky, and this is the diagonal or the diameter of the circle. So here's a circle that passes through all 4 points of the field of view. And the diameter of that circle is from one side to the other side, and half of that diameter is the field radius. So I mean, Ren is a home entertainment guy. He wouldn't have said, no, that's not the, I mean, Ren, you would have said, that's not the diameter of the circle passing through the 4 points. That's the diagonal of the screen.
Yep.
Would you?
Yeah.
Because that's how you measure the diagonal. You go from corner to corner. Am I right,
Yep.
or am I right?
You're right. Yep.
And so think of it however you want. It's the diagonal, or the diagonal of the field of view, or the diameter of the circle that passes through all 4 corners. Either way you think about it is fine. And you take half of that, and that gives you the radius. So take d divided by 2, and that'll give you the field radius.
Well, you still have to find the, if you're working from your sensor, you still kind of, well, I guess we work backwards. You still have to find the hypotenuse, though.
Yeah, you have to find the hypotenuse, and luckily there's a guy named Pythagoras.
Not around anymore.
Yeah, he's not around, but he's a really useful guy to know if you want to know about things like this. You have L, you have W, and you have D, and you have a right triangle. You say, well, Merry Christmas. D squared is L squared plus W squared. C squared is A squared plus B squared. You take the square root of that, and that gives you D. Easy peasy, right?
Yeah.
And then once you have D, the full diameter or the diagonal or whatever you want to call it,
Yep.
then you take D divided by 2, and that gives you your field radius.
That's easy peasy. Dividing by 2 isn't too hard.
R equals D divided by 2. And so you can check this formula. You can plug that number in here and this number in there, find D, divide it by 2, and that'll give you the field radius of 0.52.
Nice.
That's what we do in our observing target list. We have a photo, a favorite Astrobin photo of each object that we're interested in shooting, and we include its field radius, which you can just read. You don't have to do the calculation. Astrobin does the calculation for you, and we just have that listed in there. And if it's around 0.52, then that says that the Celestron with our camera would be a good choice for shooting it.
Good choice.
Yep.
Yeah.
Thanks for watching.
And we'll see you next time.